You will certainly have heard in school that energy is conserved in closed systems, but why must this be true? This miraculous idea which supported so much of classical physics can't just be taken for granted. In this video, I will discuss the basics of Lagrangian mechanics, a powerful approach to understanding physical systems, and the consequence of such a method, namely conservation of energy. But what is Lagrangian mechanics? Well, let's consider a system of a particle Q with position Q and mass m. The particle will have a potential energy V, which will be dictated by what system we choose to model. For instance, if we consider the gravity of a planet like Earth, this potential energy would be a radial field around the planet. We're interested in how the particle moves between times TA and TB, and we'll assume it's travelling from point A to point B. Now we have set up our system, we can define the Lagrangian. L equals U minus C, where U is the kinetic energy of the particle, and V is the potential. L depends on the position of the particle Q, the velocity, which is the derivative of Q with respect to time, which we would denote with a dot, and time itself. We also define the action of the path the particle follows, I, as the integral from TA to TB of the Lagrangian with respect to time. Notice how the action takes in a function as its input, i.e. the path of the particle. As a result, this is no ordinary function. We call it a functional, and by convention, we use square brackets around the input to show this. But how does this help us find what path the particle will actually take? To achieve this, we need to use Hamilton's principle. The actual path of the particle is the path that extremizes the action. It might seem a little out of the blue that we should expect this to be true, but while experiments classically seem to be in favour of this idea, the deeper reason is quantum in nature. But that is beyond the scope of this video. One way you might get a hint that quantum mechanics is involved is by observing the units of action, joule seconds, the exact same units as Planck's constant. But action is not a simple function, so how are we supposed to find its extreme points? Well, recall from calculus that extreme points occur when dy by dx is 0. We can use Taylor's theorem on a function to see that y of x plus h minus y of x is h dy by dx plus h squared onto 2 squared y by dx squared, plus some higher order terms. Clearly the term which is first order in our small change h is the derivative, dy by dx, and at such an extreme point this is 0. This motivates the following idea. We perturb the action with a small change, find the term first order in this small change, and then set that equals to 0. We'll denote the small change delta q of t, and we'll enforce that it is 0 at our start and end times, so that we don't change the start and end point of our perturbed path. Now delta I is I of delta q minus I of q, which becomes this integral. This is a function which has had a tiny change minus the original function, so we can use Taylor's theorem here as well, now in multiple variables, to expand this. Here the q sub I denotes the ith coordinate or index of the position q, and we adopt Einstein's summation notation that states if we have an index repeated, like how this expression has I appear multiple times, this means we sum over all the indices. We also get many higher order terms from Taylor's theorem, but since we're only interested in the first order term, we'll ignore these. We will now perform integration by parts on the second term, by integrating delta q dot I, and differentiating the other term. This gives us a new integral, and this boundary term. Recall we set delta q to be 0 at TA and TB. This means this boundary term vanishes, which makes our life a lot easier. Now we can factor out delta qi from our integral, giving us a term which is first order in our tiny change. We have essentially found the derivative of our action. We will call this the functional derivative of I, and denote it delta I by delta q. Recall we are searching for extrema of our action, so we set the functional derivative equal to 0. This is the Euler-Lagrange equation, a second order differential equation for q, the path we are interested in. I mean to solve this for all of the indices of q. If you've made it this far into the video and you're enjoying, please consider subscribing, as I'll be releasing a second part to this video soon, and hopefully you'll enjoy that too. Let's try a sanity check to see if this recovers the paths we expect. Recall the definition of the Lagrangian, and let's suppose V is a function only of position q. Now, U is the kinetic energy, so U is a half mq dot squared. Now let's compute the derivatives of L. dl by dqi is minus dv by dqi, as only V depends on position, and dl by dq dot I is mq dot I. as only kinetic energy depends on the velocity. If we substitute this into our Euler-Lagrange equation, we obtain the following relation. We can swap to vector notation to make things more obvious, and recall that mq dot is the mass times the velocity of the particle, otherwise known as the momentum, and minus the gradient of v with respect to position is the force on the particle. With this we obtain F is dp by dt. This is Newton's second law. Note that if m is constant, dp by dt is ma, and we obtain F equals ma, which is a more common statement of the law. Now let's suppose a Lagrangian has no explicit time dependence. This means that if we hold everything but time constant, then take the derivative with respect to time, we get 0, which can be written in terms of this partial derivative. Now let's consider the full derivative of L with respect to time. By the chain rule, we obtain this expression, which we can write like this. Note that this does indeed hold, as the final term can be expressed as q double dot I dl by dq dot I plus q dot I d by dt dl by dq dot I. Now, by assumption, dl by dt is 0. Likewise, this term is simply the Euler-Lagrange equation, which we know is 0, so the expression becomes this. Collecting the terms into the derivative and integrating with respect to time gives us that this quantity is constant, as it had 0 time derivative. And I'll suggestively denote this constant E. Since this is constant, it is conserved over time and cannot change. L essentially encodes the laws of physics in the universe we are trying to model. From observations, it appears that the laws of physics do not change themselves over time. This means L will have no explicit dependence on time, like the case we just looked at. We say the universe is time translation symmetric. Now, once again looking at our expression for L, let's analyze this term in our conservation law. It reduces to this, just twice the kinetic energy. Now let's substitute everything into our equation for E. It reduces to just kinetic energy plus potential energy. Clearly E is just the total energy of the system, so energy must be conserved. This turns out to be a specific example of Noether's theorem, which states that every continuous symmetry of the action of a physical system with conservative forces has a corresponding conservation law. Just by observing the laws of physics remain constant over time, we have derived conservation of energy. This reflects the deep link between symmetry in our universe and the physical features that arise from it.